Every single day, we're all living inside this giant forecasting machine, and we don't even realize we're using it.
Mhm.
You don't need a degree in statistics to predict if that last cup of coffee is going to get you through the afternoon.
Right. Or if the bus that was late yesterday will probably be late again today.
Exactly.
And that inherent human ability to use patterns from the past to figure out what happens next, that's exactly what data science formalizes into what we call time series forecasting.
Okay, so let's unpack this. We've pulled together all this source material on everything from, decades-old statistical models to the absolute latest AI breakthroughs.
Huge range.
It is. So our mission today is to give you a shortcut. We are deep diving into what makes time series data so uniquely powerful. We're going to trace its path from those simple, reliable workhorse models like ARIMA
The classic.
all the way up to this cutting-edge shift toward deep learning and these massive foundation models that are just completely transforming prediction.
And I think what's so crucial to understand right from the start is why this data is so special. It's not like a regular spreadsheet where every data point is, independent.
Right.
Time series data has memory. It has this inherent dependency. Today's closing stock price isn't random. It's heavily influenced by yesterday's price and last week's and so on.
So that connection, that's the key.
It's the core challenge and the core power of this entire field.
So why should someone who isn't a data scientist really care about understanding all these models? What does this actually mean for the real world?
Well, it translates directly into efficiency and really foresight across every major industry. Look at retail, supply chain management.
Okay.
If a company can accurately forecast demand, they can fine-tune their inventory. So they stock exactly the right number of those must-have toys.
Just for the holidays, yeah.
Exactly, right before the holidays. They avoid costly overstocking, or worse, missing out on massive sales.
Or you can think about the infrastructure that, keeps our entire world running.
Absolutely. The energy sector. Power companies are running these models constantly. They forecast electricity demand minute by minute to make sure they generate just enough energy.
So you don't get blackouts.
You prevent blackouts, you save huge amounts of fuel, you reduce strain on the grid. And then, of course, there's finance. Using these tools to anticipate market trends, execute instant trades. That's the engine of algorithmic trading.
Basically, if you can measure it over time, these insights are mission critical.
You got it.
That makes perfect sense. So before we get to the algorithms themselves, let's look at the raw material. What exactly are we dealing with data-wise?
So if you want to get really formal about it, a time series is just a sequence of ordered pairs. We usually call them T, TM. T is the time, could be minutes, days, decades, whatever, and V is the value you observed at that specific point. It could be a stock price, number of website users.
Daily rainfall.
Anything. The key is that it's ordered by T. That's non-negotiable.
And the first, most fundamental distinction you have to make is about the scope of your data. We have two main flavors here that basically dictate your whole strategy: univariate and multivariate.
Yeah, that's the most important first decision. A univariate time series is the simplest form. It just tracks one single variable over time. So if you're analyzing, say, the daily temperature in Chicago, that's univariate.
You just have one stream of numbers.
Just one stream. But the world is rarely that simple, right?
Right. Most things interact.
And that's where multivariate comes in. It records two or more variables that change together, and their interactions are what matter. Think about a smartwatch logging your acceleration on the X, Y, and Z axes all at once.
Ah, I see.
Each timestamp holds a whole vector of values, and your model needs to understand how they influence each other.
And that choice immediately shapes your entire approach. Now, speaking of approaches, forecasting, just predicting the next value, is actually only one piece of the puzzle, isn't it?
Oh, absolutely. Forecasting answers what comes next. But there are 4 other critical families of problems you can solve.
Okay, let's start with classification.
So classification is all about pattern recognition. You're assigning a label to a whole chunk of time series data. In healthcare, this is vital. A model might look at a 10-second ECG reading and immediately classify it as healthy or arrhythmic.
It turns that squiggly line into a clear decision.
Exactly. Then you've got the detective work, anomaly detection.
Which asks, is something weird happening right now?
Precisely. This is huge for security, for maintenance. If a user normally spends $500 a week and suddenly there's a $10,000 transaction at 3 a.m. from a new country,
That gets flagged.
instantly, as a potential anomaly, fraud.
And what about when the underlying behavior itself changes?
Yes, that's segmentation, or change point detection. It's about finding exactly where the behavior shifts. You want to detect the precise moment a machine goes from normal operation to, uh-oh, beginning of failure.
I see. Or finding the exact day an ad campaign started working.
You've got it. And finally, there's similarity search, or clustering.
Which asks who or what behaves alike.
Yeah. Retailers use this constantly. Instead of forecasting for 500 individual stores, they'll group the 50 stores in, say, similar urban areas that share the same sales trends. It's just so much more efficient.
So knowing which of these 5 problems you're solving is really step 1.
It's the bedrock.
All right, so once you know the problem and have the data, then we get to the algorithms. And you really can't talk time series without talking about the foundation, the statistical workhorses.
Absolutely. I mean, these models, they view time as this pure mathematical combination of repeatable components, trend, seasonality, and random noise.
And the most basic one is the moving average.
Right, the MA. It just smooths things out by averaging the last few observations. It's simple, but it only really works well when the data is just kind of bouncing around a stable center point.
The minute things start trending up or down, though, it just lags behind.
It does, and that's where the smart refinement comes in. Exponential smoothing, or ES.
How is that a step up?
Well, exponential smoothing is way smarter because it weights the past. It recognizes that yesterday's data point is probably more relevant than the one from 3 weeks ago, so it gives more importance to recent observations.
Says it's faster to react to changes.
Much faster capturing those short-term shifts. It's often the first stop for simple, reliable forecasting.
But the undisputed heavyweight champion, the one everyone learns, is ARIMA. Autoregressive integrated moving average. It sounds so complex.
It does, but think of ARIMA as the first model that successfully combined pattern recognition with a self-correction mechanism. It has 3 blended parts. The AR autoregressive part looks at the memory in the data, the dependence between an observation and a certain number of previous ones.
Okay, so that's the pattern part. What about the I, the integrated part?
That's the crucial step that stabilizes everything. The real world has trends, right? Prices go up, populations grow. The I part uses differencing to remove that trend, turning a noisy upward-sloping line into a stable, flat line that's way easier to model.
It's like pre-processing the data for the model.
Exactly. And finally, the MA, or moving average component, corrects the model's own past mistakes. It looks at the errors from previous predictions and factors them in to minimize future errors.
So it's a self-improving engine.
In a statistical sense, yes.
And if you have repeating cycles, like, say, annual spikes in airline passengers, you don't just use ARIMA, you use SARIMA.
Right, seasonal ARIMA. It's essential because standard ARIMA can't really see those big recurring cycles. SARIMA just explicitly adds parameters to handle those seasonal patterns. It's perfect for anything tied to a calendar.
But all these classic models, they see the world as linear. They struggle with complex external things like a hurricane or a competitor's big sale.
And that's the bridge to modern machine learning. ML lets us model nonlinear relationships. It stops assuming the world moves in straight lines and starts seeing the curves, the sudden jumps, the interactions between thousands of factors.
And the standout model here, the one that wins all the competitions, is gradient boosting.
Oh, absolutely. Frameworks like XGBoost and LightGBM are just dominant. They are so robust. They combine the output of many weak little models like decision trees into one super powerful, accurate prediction. They're amazing at handling multivariate data. You can throw in weather, holidays, interest rates, and the model just synthesizes it all.
But then data get even bigger. Millions of IoT sensor readings, entire financial histories, and even those ML models started to hit a wall.
And that's the moment deep learning really stepped in. These models, with all this computational power, could just automatically learn the patterns directly from the raw data. They could spot both the short-term rhythms and these really critical long-term dependencies that the other models just missed.
We hear transformer all the time with language models. How did that architecture jump from text to time?
It's a great question. So older models, like LSTMs, process data one step at a time, sequentially. Like reading a book. The transformer changed all that. It uses an attention mechanism that lets the model look at all past data points at once and decide which past event, whether it was yesterday or a year ago, is most relevant for predicting what comes next.
It understands deep context.
Deep, far-reaching context. And, training these from scratch is just impossible for most people, which is why the idea of transfer learning using pre-trained models is so revolutionary.
It's like getting a master carpenter's toolkit instead of having to make your own hammer.
That's a great way to put it. You start with a model that already gets the general rhythm of how things change. For instance, take Profit from Meta. It's designed specifically for business and web traffic data, and it's famous for being really easy to use.
What makes it so popular for, say, a business user?
It automatically breaks the series down into 3 parts you can actually understand: the long-term trend, any repeating seasonality daily, weekly, yearly, and the impact of one-off holidays or events. So your CEO can ask why the forecast dropped, and Profit can literally point to the holiday component.
That's powerful. And then you have more specialized deep learning models like the temporal fusion transformer, TFT, and NBeats.
Right. So TFT is built for multi-step forecasting, predicting the next 10 days, not just tomorrow. And its key strength is that it's still partly explainable. It'll tell you which features, like price or weather, mattered most for its forecast.
So it blends power with clarity.
Exactly. And NBeats is another powerful neural architecture just for univariate data that's famous for getting extremely high accuracy across all kinds of different data sets, from finance to energy.
Okay, that brings us to the biggest question in this space right now, the viral one. People hear AI, they think ChatGPT. Can an LLM actually predict the price of a stock next week?
This is the ultimate aha moment, and we really need to clarify it. The answer is no, not directly. A traditional large language model like ChatGPT is trained on text, on language, grammar, human writing. It's an expert in reasoning and conversation. It is not fundamentally a mathematical engine built for crunching numerical sequences.
So if I paste a year of sales data in there and ask for a forecast, what's it actually doing?
It's acting as an incredibly smart interface. It converts your numbers into tokens, understands what you want, and then using its code execution tools, it calls a pre-existing specialized algorithm, like ARIMA or Profit, to do the actual math.
I see.
The LLM's job is to intelligently set up the analysis and then explain the result in plain English. It's not doing the forecast itself.
Which means the real revolution isn't in generic LLMs, it's in these specialized models that are fluent in time. The time series foundation models, or TSFMs.
Precisely. TSFMs are the future. They aren't trained on language. They're trained on billions of real-world time series from finance, healthcare, IoT, every industry. They build a general shared understanding of the physics of how things change over time.
And the next evolution, which we're already seeing, is the true time series LLM. This blends that numeric focus with the reasoning of an LLM.
Yes. These TSLLMs are transformer models trained on massive, curated time series datasets. And this unlocks totally new things, like conversational forecasting. You can ask complex questions like, forecast next quarter's demand for our top 20 products and explain the drivers.
And it can explain anomalies.
In plain English. Instead of just flagging a drop, it might say, Store B's revenue dropped 20% on Tuesday because local records show a public holiday closure.
That is a game changer. And when we talk about models like Amazon's Chronos or Google's Times FM or Time GPT, these are the models making that possible.
And the concept that underpins all of these is the idea of global models. So historically, if a retailer had 1,000 products, they'd build 1,000 local models. One model just for product A, another for product B. It's slow and resource intensive.
And if product A has only been selling for 3 months, that model has almost nothing to learn from.
Exactly. A global model flips that entirely. It's one single massive model trained on all 1,000 time series at the same time. It learns the common patterns and shared rules that govern all of them.
So instead of 1,000 little cookbooks, you have one giant culinary encyclopedia.
Perfect analogy. The big advantages are efficiency and better generalization. If product A only has 3 weeks of data, the global model can still make a great prediction by borrowing what it learned from the other 999 products. It understands the general weekend uplift or the holiday dip.
It's that cross-series learning.
That is the secret sauce.
Okay, let's pivot from architecture to the practical reality of making this work. Because no matter what model you use, from classic ARIMA to futuristic Time GPT, they can't fix bad input. We have to talk about data prep.
This is the cleaning the lens step, and it's where most projects fail. The first thing is rescaling or normalization. If you have 2 variables, say electricity usage from 1,000 to 50,000 and temperature from 0 to 100, the model will just assume electricity is way more important because the numbers are bigger.
So you scale everything down.
You scale everything down, usually to between 0 and 1 to level the playing field.
And you often run into gaps in the data, missing values.
You can't have gaps. So you have to handle missing values using things like interpolation, where you estimate the missing point from what came before and after. We also do resampling a lot, turning messy, irregular logs into clean, standardized intervals like hourly data points.
And because this is supervised learning, you have to teach the machine to look at the past to predict the future. You can't just feed it a continuous line.
That's where the essential technique called a sliding window comes in. It's a simple idea. If you want the model to predict the next day based on the past 7 days, the sliding window just moves across your timeline, creating hundreds or thousands of these little input-output pairs.
So the model sees it as a bunch of self-contained examples.
Exactly. 7 days in, 1 day out, it learns that dependency.
Now, once the data is clean, sometimes the raw numbers aren't quite enough. You can actually enhance the data by extracting features, right? Turning those raw signals into gold.
Yes. For traditional machine learning models like XGBoost, you don't always want to feed it the whole raw time series. You want to summarize its nature. A great tool for this is Catch-22.
Catch-22.
It's the collection of 22 carefully chosen statistical features. So instead of reading the whole series, the model gets 22 numbers that describe the series' behavior. Its mean, its variance, its predictability, its complexity. It's fast and interpretable.
That makes sense for traditional ML. But
Yeah.
what if you want that deep learning performance without the huge cost and complexity?
That's where Rocket comes in. It stands for Random Convolutional Kernel Transform. It's a brilliant shortcut.
Okay.
Instead of training a massive network for weeks, Rocket applies thousands of random, simple convolutional filters to the series extremely quickly. These filters extract useful features, and you then feed those features into a simple classifier.
So you get the feature extraction power of a deep network without the training.
You get near deep learning performance, but it trains thousands of times faster, and you don't need expensive GPUs. It's the closest thing to a magic trick we have for time series classification.
That is a huge aha moment. Okay, finally, we can't wrap this up without talking about the plot twists in the data, the anomalies.
Anomaly detection is fundamental. It's about flagging moments that break the usual rhythm before they become a crisis. We usually look for 3 types.
The simplest one first, the point anomaly.
That's a single glaring observation. It's a $10,000 transaction when the average is $50. It just sticks out.
Then the trickier one, the contextual anomaly.
Right. Here, the value itself is fine, but the timing is weird. High ice cream sales in July. Normal. The same high sales on Christmas Day in northern Canada. That's contextually anomalous.
The context violates the expectation.
It does. And the third type is the collective anomaly. This is a group of points that form an unusual pattern together, even if no single point is that weird. Think of a slow, steady temperature rise in a server room over hours.
No single reading is an alarm, but the trend is the problem.
The collective pattern indicates overheating.
So how do modern systems spot these subtle shifts?
A lot of them use deep learning models like the autoencoder. You train an autoencoder only on normal data. It learns how to perfectly reconstruct those typical patterns. So when it sees something abnormal, an anomaly, it struggles to reconstruct it. That creates a huge reconstruction error.
And anything it can't perfectly mimic gets flagged as the plot twist.
Exactly.
What a fantastic journey. We've gone all the way from the data's inherent memory and the elegance of classic AREMA, across the bridge of machine learning, and straight into the future with these huge foundation models.
I mean, the whole field is clearly moving towards systems that fuse that linguistic intelligence with real mathematical precision. And this knowledge, it doesn't just let you look backward. It lets you ask better, more targeted questions about the future.
Not just what happened.
But why did it happen, and what specific factors might drive what happens next week?
It really does change your perspective on the world. This whole field reminds you that everything around us just operates on a rhythm. Every market swing, every heartbeat, every traffic pattern is a sequence just waiting to be understood.
A story of change told in numbers. And now, you know how to decode that rhythm and really listen to what the data is saying.